Hey folks, welcome back to Bennett's Chemistry 12 tutorials. Today we're going over the electromotive force, or the E cell electrical potential of a redox reaction, and the determination of whether or not a redox reaction will be spontaneous or not. Okay, now as you can see over my shoulder here, this is just part one of this concept. We'll do an introductory type of lesson today. Go over one fairly straightforward, simple example. And then in part two, the next video that I do, we'll expand out a little bit more into more complicated situations and look at a little bit more of the deeper details. Okay, so this will be more of an introductory concept here. Okay, so quick review of redox reactions. Redox reactions actually have two parts to them, two halves as they were, half cell reactions as they're called. And so there's the oxidation half and the reduction half. So the oxidation would have a chemical that has an atom which will lose electrons, and those electrons will be transferred to a different chemical, and the electrons will be transferred to an atom of that chemical, and that chemical will reduce as a result of it. And so for every redox reaction, you have to have both parts. You can't have just an oxidation, because you can't just give up electrons and they go nowhere. They have to go to another atom. Okay. Now, terminology-wise, let's quickly remind you of the terminology. The chemical that actually has the atom that oxidizes will be called the reducing agent, because if something oxidizes, that means it forces or it causes another chemical to reduce. And that's why it's called an agent, and vice versa. If the chemical that reduces, because it's reducing, it is an oxidizing agent. It causes another chemical to oxidize. Okay, so you have to know that, because the terminology is critical, because you'll talk about oxidizing and reducing agents, and you have to know that when I say oxidizing agent, that actually means the thing that's reducing. And it's also the table that we're going to use, the reference page that we're going to use, will refer to things as oxidizing and reducing agents. Okay? Okay, so what is this concept of the E cell? So electrical potential it's a physics term, so the potential for an electron to go from A to B, essentially. And so it's measured in volts. And so a voltage difference between two places is what's known as the electromotive force. It's what's driving electrons to go from A to B. The bigger the difference, the bigger the potential difference, the stronger the electromotive force. Okay? Now, chemistry, if you're talking about an reducing agent and an oxidizing agent coming together, the thing that's oxidizing is giving up electrons, and the electrons are going from that thing that's oxidizing to the thing that's reducing, which means that there is a potential difference between point A, the thing that's oxidizing, and point B, the thing that is reducing. And that difference in the electrical potential is actually measured in volts. Now, if you were talking about just one atom and one atom, obviously that's a very low voltage. But if you start talking about things in moles, and you start talking about numbers of chemicals, numbers of molecules and atoms in terms of moles, now you're talking about many more electrons. And so the electrical potential, obviously, the actual electromotive force actually can be quite strong when you start talking about numbers like that. So that potential for electrons to go from the reducing agent to the oxidizing agent, that potential is going to be measured in volts. That is known as the electromotive force, or it's known as the E cell, okay, the electrical potential difference. Now, in the title up here, you'll see that there's a little, it looks like a degree symbol. That's it means naught. And by putting the little E naught of a cell, that means standard conditions. So E naught means under standard conditions, this is what the electrical potential will be. So, and we'll get into a little bit more what standard conditions actually means when we're talking about redox. We'll get to that one later on when I show you the table. Okay, so before we kind of get going, I want to talk about just the general concept of spontaneity and not spontaneous, and the electrical potential or the difference in energy. Okay, and so I'm going to draw a visualization, an analogy on the board that has nothing to do with chemicals, but you'll kind of get the sense of what I'm talking about here. So I'm going to draw this little analogy. Let's pretend there's the ground. Let's pretend I put a box on the ground. And I'll label it. I'll label it A. So I put a box on the ground, and what I'm going to do is I'm going to put another box on the ground, and then I'm going to connect the two of them with a ramp, and I'm going to put a bowling ball on top of them. Okay, so it's a pretty simple, straightforward thing. Trust me, you're not going to be challenged understanding what's going on here. I'm not trying to trick anybody. So I put another box here, but that box is shorter. Okay, and then I'm going to put a ramp connecting the two. Okay, so just a piece of wood. And then I'm going to ask you this question. If I put a bowling ball on the ramp up there at A, and I put the bowling ball up there, I'm going to ask you two questions. I'm going to say, okay, so if I put the bowling ball right here, okay, so there's the bowling ball. So if I put the bowling ball right there, two questions. One, will it roll? Like, just if you let go and just let nature take its course, will it roll? And B, how much damage would it do down at the bottom? Like, if you put something down here, like, I don't know, your little brother or something down there on B, how much damage would it do? Meaning, how much force would it be able to or how much energy would it be able to transfer to some object that was sitting down there? Okay, so you look at it and you go, well, okay, number one, it's downhill, so duh, gravity's going to pull the thing down the hill. So it will, if you let nature take its course, it will roll down that hill, okay? So that means it will spontaneously roll from the top of A to B. How much damage? Well, I guess it's relative. I mean, I don't know, a certain amount of damage. It's rolling, so it's going to hurt. If you were sitting right there, it would hurt, a bowling ball hitting you. But, I mean, I don't know, it's relative, isn't it? So what if, okay, fairly straightforward, like, yeah, it rolls and it will cause some damage. So what if, instead of that, I make A much taller? I put the bowling ball up there. Okay, same two questions. Okay, so A, if I just let nature take its course, will it spontaneously roll? And I think the answer would be yes, it's rolling downhill. As long as it's not teetering up there, you put it so it actually goes. So yes, it will roll. How much damage will it cause when it gets down to B? Well, now, again, you don't know how much exactly, but you know it was more than before. And your logic tells you that if that difference between the two of them gets bigger and bigger and bigger, the bowling ball is going to have more momentum, I guess, is what it's going to have. It's going to have more momentum. When it gets down to the bottom, it's going to have more energy to unload onto whatever's sitting down there. And so that difference, the relative difference between the two of them is really important. So I just made A really big. Well, what if I made B really big as well? Well, is the ball still going to roll? Yeah, because A is still taller than B, but it's not going to roll very fast, so it's not going to do a whole lot of damage once it gets over to B. It's not going to have very much energy. Because the difference between the two of them, even though A is really a tall box, so is B. And so the relative difference is not very big. That is critical. So the relative difference difference between the two things makes a difference. It still is spontaneous because it's still downhill. What if I make B taller than A? And I ask the same question, will it spontaneously roll from A over to B? And how much damage will it, or how much energy will it have when it actually gets there? And damage does it do? And you'll say, well, it's uphill. Like, it's not going to roll. If you just let nature take its course, it's not going to roll from A to B. That's not how gravity works. It doesn't make things go uphill. It makes things go downhill. So this will not happen spontaneously. Some of you may be thinking, and wise if you are thinking it, because it's actually later on, once we get into electrochemistry, that you can make it go from A to B, right? If you pushed it or rolled it up the hill or threw it hard enough or whatever, you gave it a force, you can make it go from A to B. Okay, so this situation is a non-spontaneous situation. The ball is not spontaneously going to go. The other ones were, because they would spontaneously roll downhill with nature. So when we're talking about redox reactions, a spontaneous redox reaction will have the transfer of electrons, just like the gravity pulling the bowling ball downhill. The transfer of electrons will happen spontaneously from chemical A to chemical B. If it is a non-spontaneous reaction, then the electrons will not transfer spontaneously from A to B. Now, as you will learn, as I was saying, you can make electrons go from A to B, even if it's a non-spontaneous thing. And we'll get into how that works and what the application of those things are. And you probably already in your head can probably think of one. You probably use them just about every single day. Rechargeable battery in your phone. So the idea here is that the difference is key, and then like the direction of the ramp is really key as well. Now, I'm going to ask you this question, because I was asking A to B. Well, what happens if I put the ball, because A to B, it didn't roll spontaneously, but what if I put the ball up here? It would roll spontaneously from B back to A. So if it was non-spontaneous in one direction, it is spontaneous in the other direction, right? It's just a ramp. So depending on which end of the ramp that you're going from, it's either spontaneous or not spontaneous. And then in the opposite direction, it's the opposite. So in the other ones where I had B lower than A, and it spontaneously rolled from A to B, well, in the reverse direction, it was non-spontaneous. That, again, is very critical. So if electrons will transfer spontaneously from chemical A to chemical B, they will transfer non-spontaneously from B back to A. And if it's not spontaneous from A to B, it'll be spontaneous from B to A, which is, that's an important concept to grasp as well. Notice as well that if it was non-spontaneous, if I put the bowling ball over here on A again, it was non-spontaneous going from here to here because it was uphill. So it was non-spontaneous. And it was spontaneous going the other way. But the heights of the two boxes, A and B, are still the same height, no matter where you put the ball. The A and the B are the same height. The difference between the two of them is always the same. Always, no matter what. And so all that really matters is what direction is the ramp going. Is it going up or is it going down? But the magnitude of the difference is always the same for these two chemicals. Again, that's a critical thing to remember, okay, is that the magnitude will stay the same, but the direction might be different. So up, down might be positive, negative, okay, and that's kind of what you're going to see. Okay, let's go back to our somewhat original diagram. So they're a little bit taller than what I originally had them. Okay, so this was an analogy. Okay, if we were talking chemistry, this would be an analogy for what a redox reaction is doing. So what are all the different parts? What is the bowling ball? What is A and what is B? And what does the ramp kind of represent? So let's first of all talk about the ramp, because the ramp would be an abstract thing, as a matter of fact. The ramp would just be the actual physical connection between the two, the collision, as it were, between chemical A and chemical B. what would the ball be? What would the bowling ball be? Well, it's the thing being transferred from box A over to box B. So the thing being transferred in a redox reaction are the electrons. So in this analogy, the bowling ball would represent the electron or electrons, plural. Because the ball is going from box A over to box B, like it's like box A is losing the bowling ball, box A must represent the reducing agent, the thing that oxidizes. Okay, if you oxidize, you're a reducing agent. So it loses the bowling ball, and so the bowling ball represents the electrons. That thing, box A, is the thing that's oxidizing, and therefore the reducing agent. That leaves box B to represent the oxidizing agent. Okay, so that's what all these different parts are. So A and B are actual chemicals, and the bowling ball is the actual transfer of the electrons. And spontaneous versus non-spontaneous, I mean, it has nothing to do with height and gravity, but it does have to do with electrons going from a less favorable to a more favorable position, let's say. And gravity, the reason things fall is because it has a lower potential energy, and so the ball would have a more favorable position to be over here on B, because it has less potential energy then, because it's lower. Okay, now that's kind of the general gist and the segue into the chemistry part. But before I even do that, what if this is a critical concept? Hopefully you've already gotten this concept, actually. This concept's actually quite important. What if I said, okay, here's box A. I'm going to put a ramp over to box B, and then I'm going to put a bowling ball on, and you're going to tell me if it's spontaneous or not, and how much energy it will have when it gets to box B. Okay, so answer the question. And you kind of looking at me going, okay, so go ahead, draw box B, put the ramp on, and then I'll be able to answer the question for you. Well, what if I just sat here and didn't draw box B? You'd say, well, you're a moron. Like, figure out that this is a relative thing. You can't tell me if it's spontaneous or not until I see where the height of the box is. Once I know where the height of the box is, I then know, relatively speaking, A, if the ball will roll in the first place, and B, how much energy it might have when it actually gets over to box B. But you need a partner, and it needs to be relative to each other. And this is really critical, actually, when we start using the reference table that we're about to use, is that you have to recognize that everything is going to be relative to each other. Okay, and that's very, very critical in that we understand that concept. Okay, so here's the idea. I'm going to ask a question, okay, and I'm going to frame the rest of the class on this one question and the use of the table and what it all means and everything, based on this one question. So the question is, okay, will the following redox reaction occur spontaneously under neutral, standard conditions. And let's see, I want to make sure that we don't. Okay, so the reaction is mercury 2 nitrate, aqueous form, put a piece of tin into the solution of aqueous mercury 2 nitrate. And then the question is, will it spontaneously react to form tin 2 nitrate and liquid mercury metal kind of floating around? So number one, this reaction is really kind of cool if you actually get a chance to do it. You probably won't be able to because mercury isn't allowed in schools anymore. But if you do, it's really kind of cool because you get this silvery liquid forming. Actually, you're going to find out it's spontaneous. So it's kind of cool. Anyways, so how do you go about doing this, right? Like all I've shown you so far is this analogy of a bowling ball rolling from box A to box B. So how do you translate that analogy into chemistry and try and determine if the ball rolls naturally, meaning the electrons move naturally? Okay, so what you need to do is you need to find out what is the electrical potential for the electrons to move from A to B. And so obviously something over here is A and something over here is B. One of the two things is going to oxidize and one of the two things is going to reduce, right? So they'll represent the A and the B boxes in my analogy. So I guess we better figure out which one is which. Okay, so we need to do that. So that's part of our strategy. The other thing that we need to do is we need to have some numerical form of an electrical potential for each of those processes to occur. And so that when I combine them, I can look at that value that I get as a E0 cell. Okay, so you've got a half cell reaction. So that's the reduction and the oxidation. You put them together, that's the whole cell. It's not a half cell anymore, it's a whole cell. So what we're asking for with E0 is the standard electrical potential for the whole reaction. So the two halves put together. So how do we go about doing that? Where do we look? Okay, so let's take a little bit of a break here and let me introduce you to the table, okay? The table that you're going to need. And the table that you're going to need, again, you'll have one either in your textbook, maybe it's online, you can find these things all over the place. Like this is pretty standard stuff. In British Columbia, a lot of teachers are still using the data booklet from the provincial exams. And on the very last page of that data booklet is a table that says, the title is Standard Reduction Potentials of Half Cells. Okay, so that's the actual title. And then it gives you like a whole schwack of little chemical reactions down here. And you'll notice, if you look at this table, one, the printing is super small. There's no way you're going to be able to see that. So you need to have your own sitting in front of you. When I talk about this, you need to have yours sitting there. So they're really small. But the other thing you'll notice is that everything on here has electrons in it. Okay, so it has some chemical over on the left-hand side, plus electrons goes to some chemical over on the right-hand side. So the electrons are always on the left-hand side. So, and that's what you'll notice. Chemical reactions never have electrons in them. Half reactions always have electrons in them. And that's what the last kind of word says here, of half cells. So that's the first thing you have to know about this table, is that it's half cells. So let's go through this entire table first of all, and let me explain what every word means and how it all kind of translates out here. So first of all, the first one says standard. Okay, the word standard. So what does standard mean? Well, you probably remember standard temperature and pressure from when you did the ideal gases back in science or chemistry 11. So standard typically means a set of conditions. And so when you're talking about redox reactions and you're talking about this table here, you're talking about two key elements of the standard concept. Number one, it's at 25 degrees. As kind of all the things typically are in this data booklet. So 25 degrees. The second thing is that everything is considered 1 molar. A standard solution would be 1 molar of it. So if it was an ion, that'd be 1 molar of it. If it was a gas, that means you'd have a container that had 1 molar of that gas in it. If you have concentrations other than 1 molar, or temperature other than 25 degrees, you're not standard anymore. This little knot right there does not apply anymore. And so you have to be talking about 1 molar solutions, or gas concentrations, and 25 degrees if you're going to use this table. If you don't have those conditions, which is not going to happen in Chem 12 other than a scenario I'll tell you in just a sec. If you don't have standard conditions, you can't use this. You will learn eventually that there's something called the Nernst Equation. And if you take first year Chem, you'll learn this when you do Redox in first year Chem. Pardon me. And so the Nernst Equation allows you to take into consideration, or it helps you calculate the electrical potential when concentrations are not 1 molar and temperature is not 25 degrees, 298 Kelvin. So that will be learned later on. You may, and this is what I was just going to refer to, you may be asked, okay, so as this reaction progresses, what do you expect the potential to do? And so what typically happens is when the concentrations are less than 1 molar, as the reaction progresses, like the initial is a common concept. What's the initial electrical potential of this cell? Because as it runs, things run out and the potential goes down. So as this reaction runs, the potential will go down as the concentrations of things drop below 1 molar. And so you might be asked that concept. And if it's above 1 molar, then it would be greater than the standard. Okay, so keep that concept in mind. We're talking standard. The second word in here is reduction. Everything on here, as I pointed out, is in the form of a half cell reaction. And you know that because it's got electrons in there. You can see it. You can see the electrons written into the actual equation. And overall equations never have electrons in them. Only half cells do. You also know, you'll be able to figure this out, that this is written as a reduction half cell because the electrons are always on the left-hand side. And as you go down, you'll see that there's a chemical and then there's always a certain number of electrons. And the number varies depending on how many electrons it takes for that thing to actually reduce. I've drawn a very short annotated version, 2, 4, 6, 8. I put 9 lines on here. This one has obviously more than 9. This has more like 30. So I picked a few off of there to show you. And you'll see that, there's chemicals down here and then there's electrons down the left-hand side. And if the electrons are the reactant, it's not really a reactant, but they're on the reactant side, that means you're talking about a reduction. Okay? So the table is in the form of being a reduction, but use your brain. Because if you've got things in the form of a reduction going left to right, well, what if you look at it going right to left? And you can, why not? You did with the Ka table. If you looked left to right, that was the acid acting as an acid. If you looked at it right to left, that was a base acting as a base. So the Ka table was actually dual purpose. This table is also dual purpose. Every line is not only a reduction, but it's also an oxidation if you just look at it backwards. So, for example, the one at the top here, the reduction of F2 takes 2 electrons and you form 2 F minuses. That's what happens when F2 reduces. It forms F minus. You get 2 of them. But what if it's the other direction? 2 F minuses would release 2 electrons and go back to form F2. And so this is a reduction of F2, but it's also the oxidation of F minus. And that's what the columns are labeled as, right? So down the left-hand side is the oxidizing agent, the thing that reduces, and down the right-hand side is the reducing agent, the thing that oxidizes. So recognize that every single line has 2 actual pieces of information, the thing going left to right as the reduction, the thing going right to left as an oxidation, okay? So recognize that. And sometimes you're going to find, just like in amphiprotic acids, you would find an amphiprotic acid or an amphiprotic chemical on both sides of the table. Different lines, but on both sides of the table. Same here. Be really careful. Sometimes something that's over here on the oxidizing side will also be able to reduce as well. Okay? So be aware of that. So that's the second word. The third word in here is potentials. And so everything on here has an electrical potential for electrons moving. So here it is over here on the right-hand side, and then there's a number associated with it. But, and this is super, super critical, these numbers are not absolute values. So when F2 reduces to F minus, it's not as if that thing has 2.87 volts of potential energy. It matters what you put it with. So where do these numbers come from and what do they actually mean? They are relative values. Okay? So it's almost as if what's the height of Mount Everest? Well, relative to what? Relative to sea level. Okay, well, it's 29,000, whatever it is now, 29,050 feet, something like that. Well, what is it relative to the height of K2? What is it relative to the height of Denver? What is it relative to the height of the bottom of the Mariana Trench? Like, the height of something is dependent on the relative point you're measuring it from. This is the exact same thing. These are potentials relative to a point of reference. Now, you might say, well, what's the point of reference? I have no idea what the point of reference is. Well, the point of reference is whatever you set as the zero. Like the temperature scale. 0 Celsius, freezing point of water, pure water with 1 atmosphere of pressure. So 0 Celsius does not mean that the particles have zero kinetic energy. Average temperature is the average kinetic energy of the particles. So 0 does not mean zero kinetic energy. That's not what it means. It's a point. We needed a reference point to compare everything to. So you go in the positive direction, you're warmer than water freezing. You go below 0, you're colder than water freezing. It's that simple. If you want to know the point where there's zero kinetic energy, that's what the Kelvin scale was all about. And 0 Kelvin, absolute zero, was that. So the reference point is really critical here. These are all relative values, just like the two boxes. The boxes are kind of important here because where they were relative to each other was critical, right? Not just the size of one of them, it's where relative the other one was to it that was critical. So in chemistry, everything on this table is relative to the standard reduction half cell of hydrogen ions. Okay, and that's critical. And you can see it. I put it on here, and you will find it. It's on the table here. Right? It's on the table, and not only that, but on the one that we give in BC, it's actually highlighted for you. Okay, so everything's there. And you'll see everything above it is positive and everything below it is negative because it's relative to the zero. So relative to the reduction of H+, how good are these other things at reducing? And as you go higher and higher and higher, you're getting better and better and better. Sorry, the chemicals are getting better and better and better at picking up electrons and reducing. And the number over here is then relative to hydrogen. How good are you? Right? Not just absolute, how good are you? Relative to hydrogen, how good are you? So the fluorine, the F2, is 2.87 volts better than hydrogen ions at reducing. You go below it, and I go here to zinc plus 2. Zinc plus 2 ions are 0.76 volts worse, negative, worse than hydrogen ions reducing. And so the table gives you relative values, and that's critical because you want to know the relative heights of the boxes. You want to know the relative abilities of these things to reduce and / oxidize. Okay? Now, you have to tie a couple things together here. The two boxes that I had, the A and the B. Remember, the ball could roll in one direction from A to B or not roll in one direction from A to B. But if you looked at it in the reverse direction, the B to A, it was always the same magnitude because the difference in the height was always the same, but the opposite direction. Okay, so it was up or down, positive or negative. So let's look at my little chart here. So I'll choose copper for a sec. So copper ions, copper plus 2, relative to hydrogen, reduces relative to hydrogen, has a reduction potential of 0.34, positive 0.34. Okay, so A to B. Sorry, that's not really, I shouldn't use that because that's not really what the analogy was. So this turning into copper had a potential of positive 0.34. Well, what if the copper, because the line is is two values, right? So copper oxidizes back into copper plus 2. What's the potential for that? Well, it would be the same magnitude, the same difference between the two, but the opposite direction, so the opposite sign. So if it's positive 0.34 going from the ion to the metal back to the ion would have been negative 0.34 from a relative perspective. Okay, so that's kind of critical. So if you're looking at the table and all the positive ones above the H plus in the reductions, that means all of the ones oxidizing would all be negatives going the other direction. Okay, so it's like the signs flip-flop on the table if you look at it from right to left. That's kind of critical. So the table is really important to get a really good understanding of what is it good for? What does it tell me? It tells you about reductions and it tells you about oxidations, both. Things reducing on the left, things oxidizing on the right. It tells you the relative potential compared to the hydrogen, the standard hydrogen half cell, relative. Now, if two things are relative to hydrogen, then you can figure out the relative value between each other. So if you know, okay, just kind of look at this one. If you know that the F2 relative to hydrogen is plus 2.87, okay, and you know that lithium turning back to lithium plus 1 relative to hydrogen is positive 3.04, because the opposite direction, so I put a positive on it. The difference between the two of them would be you add those two things together, because they're both relative to the same standard, okay? So you know, okay, so for example, if I knew the height of, or I knew the depth of the Mariana Trench below sea level, and I knew it was 35,000 feet, and then I knew the height of Mount Everest from sea level was 29,000 feet, and then I asked you, well, how far is it from the bottom of Mariana Trench to the top of Mount Everest? Well, you know it's 35,000 deep to get back up to sea level, and then another 29,000 feet to go to the top of Mount Everest. So actually from the bottom point on Earth, really, it's filled with water, but whatever, bottom point on Earth, up to the top point, that would be 35 plus 29. That's 64,000 feet. Because they're relative, it's all relative to sea level. So you knew how to combine the two of them. This chart is exactly the same thing. Okay, so that's what we're going to end up doing. That's our strategy here. So this, back to the question now. So is this thing spontaneous or not? I need to find the potential for the reduction. I need to know the potential for the oxidation relative to hydrogen. And then I need to combine them into an overall. And I get an E cell, it's called. And the value of the E cell will tell me, will it be spontaneous, like the ball rolling down the hill? And how much energy will it have, like the actual magnitude of that? How much damage will the bowling ball do? It's the same concept. Okay, so I need the two parts. I need the box A and the box B. And I need to figure out what's the height and whether it's going to be spontaneous or not. Okay, so let's do that. So I look at the thing here. Very first note that you have to make is that everything has to be in a net ionic equation. The tables that you're going to use only have the ions on them. Okay, so it won't have HgNO3 on it. It'll have Hg plus 2. It will have Sn plus 2. It'll have NO3 minus 1. It'll have all of these things on it. But it needs to be a net ionic equation. So that's the first thing I'm going to do. So to do that net ionic equation, I take the aqueous things and I separate them into their individual ions, because that's truly what they're doing floating around in the water. So this guy is truly Hg plus 2 ions. That is truly 2 nitrate ions plus the piece of tin in solid form. The tin is truly Sn plus 2 ions plus the 2 nitrate ions and the liquid mercury. So that is the complete ionic equation. That's not the net ionic equation. So the net ionic equation will be eliminate all the spectators. Okay, so you can see that the nitrate, two of them over here, They're still over here. They're still nitrate. There's still two of them. They're still floating around doing nothing. They haven't done anything. They are spectators. They're just watching. They're not actually participating. So I erase them. And my net ionic equation then is really just the Hg plus 2 and the piece of tin turning into Sn plus 2 and the Hg. So let me just rewrite it so it looks like it's supposed to look. Okay, so that's really what happened. Mercury ions turned into mercury. Is that a reduction or an oxidation? Well, it went from +2, oxidation numbers, +2 to 0. So that's a reduction. So the reduction, sorry, that's reduction, red, reduction, is Hg plus 2 going to Hg. Okay, so if I'm balancing that half cell reaction, there are no oxygens, there are no hydrogens, it's super easy to balance. It's just, you're down to the charge. So you balance it by adding 2 electrons to it over there. Now, if you're a little worried about whether or not you're going to have the right half cell reaction balanced, you're not going to be asked this question unless the half reactions are on the table. Okay, because you need the table with the values. Okay, so sure enough, the reduction of Hg, if you just look for Hg plus 2, and be really careful because sometimes there's some trickery going on. So make sure you've got exactly Hg plus 2 turning into Hg. Go down until you find it, and it's on here somewhere. It's small. It's up here somewhere. But it's right there. You just copy it off the table. The tin must obviously be the oxidation, but it's going from 0 to +2, so its oxidation number is going up. So sure enough, it's an oxidation. So the tin is turning into Sn plus 2. Again, there's no oxygens, there's no hydrogens. It's just balancing the charge, which means +2 electrons. The overall reaction, and part of why I teach, when I'm teaching how to balance redox reactions, part of why I do the half cell method is because you're used to doing this type of balancing, where you do each reduction and oxidation half cell, you make sure the electrons are balanced, and then you come up with it. I mean, you could see that one's balanced before you even tried to do it. So it's not super difficult that way, but the electrons cancel, and sure enough, you get Hg plus 2 plus tin goes to Sn plus 2 plus Hg. Now, I'm not telling you anything you couldn't have figured out. I'm sure you could have separated it into its 2 half cells. To be able to tell what's its E0 cell, sorry, its EMF, its electromotive force, its potential difference, any of those words work, and whether or not it's spontaneous or not, you need to know the potential difference. You need a voltage associated with it. So this is where the chart comes in. So each one of these guys has its own E0 off the table relative to hydrogen. So if it's relative to hydrogen, then if each one's relative to hydrogen, then you know what they are relative to each other as well. It's just the combination of those two. And so what I need to do is I need to, whoops, I put that a little bit too high. I need to figure out what is the reduction potential for Hg and what is the oxidation potential for the Sn plus 2. So I happen to have included them on my little annotated chart over here. I knew where I was going with this. So on the chart, Hg, and you can look for it yourself if you want, just to make sure you're finding the right spot. Hg has a reduction potential, because it's just standard, off the table, the way it's written. I haven't flipped it left or right to left or anything. It's exactly as it's written. That value is plus 0.85 volts. Okay, that's what that standard reduction potential is relative to hydrogen. Now the tin. So the tin is an oxidation, which means it's the other direction. It's right to left. I've included it on here, but it's written as a reduction. I actually want to go from this. Okay, so I want to go from that. So if I'm going Sn back over to Sn plus 2, and if you're looking at it right to left, that's exactly what I've written down here. But the E, because it's negative as a reduction, that means it's the same magnitude but the opposite sign when you go as an oxidation right to left. So this must be positive 0.14, which means the overall E cell is simply the two of them added together. So the initial, whoops, so the initial E cell, again, as this reaction goes, you're going to use up the Hg plus 2. Its concentration is going to drop below 1 molar, and it will no longer be standard. So as soon as it starts reacting, it loses this. But its initial standard electrical potential is 0.99 volts. That's the difference between the two of them. Now, how do you know if it's spontaneous or not? Well, it's very quite simple. If this value comes out to being positive, if the E cell is positive, it's spontaneous. Okay, so positive, we're talking spontaneous. Negative, uh-oh, ran out of room. Negative, it's non-spontaneous. It's that simple. You get a positive value, it's spontaneous. Negative value is not spontaneous. The magnitude of it gives you a sense of how well that reaction occurs. Okay, and you can start thinking of, well, okay, so what is a 1.5 volt battery? What is a 3 volt battery? And is it a combination of chemicals that actually provide a certain potential? And yeah, we do, and you'll see that when we get into there, the application of this stuff is you get certain potentials when you actually have the reduction and the oxidation of specific chemicals that we use in our batteries. Okay, so spontaneous positive, non-spontaneous negative, and it's really that simple. So one of the critical things to know is the oxidation half cell, you're always flipping the sign. Okay, always. The reduction stays exactly as the table says. The oxidation is always switching the sign. It's not always going to come out positive. Sometimes it's going to be negative. Sometimes the reduction will be negative. Don't worry about that. Just add them together and see what you get. And if it comes out negative, it's non-spontaneous. Positive, it's spontaneous. Now, another little trick that I like to do, and I'll show you with my makeshift ruler here. If you've got your table, if you take the chemical that is reducing and the chemical that is oxidizing, and you circle them, or you highlight them, or you just point at them with your finger. So I was taking Hg plus 2, right? Hg plus 2 and tin. So there's Hg plus 2, there's tin. If you take a ruler and you connect those two, if they form that angle, they are going to be spontaneous. If the thing that is reducing, okay, let me put it a different way. If the thing that is reducing is above and to the left of the thing that is oxidizing, it will be spontaneous. How far above and to the left will determine kind of how well it's going to react and what the electromotive force is going to be. So copper plus 2 would also react spontaneously with tin. H plus 2 would react spontaneously with tin. Not quite as much, but it would still react spontaneously. Therefore, if you go an angle going the opposite, let's say I take tin and I reacted it with aluminum. Okay, so the angle is now opposite. Like it's the aluminum, the thing that is reducing, is no longer above the tin line, it's actually below the tin line, which means this is going to be non-spontaneous. If you do the math and you get the E cell, it's going to be non-spontaneous. But it's a good little way of just taking your pen and, okay, spontaneous is this way, non-spontaneous is this way. Good. Okay, a little trick just to quickly tell. Of course, you need a number to prove that you're talking spontaneous and not spontaneous. But it's a good little trick if you just have to do it quickly. Will it spontaneously react or not? Yes or no, type of thing. Okay, so when we come back next class, what I'm going to do is I'm going to go through a couple more challenging situations and look a little deeper at some of the details that might apply here. Okay, so acidic solutions and what happens if it's, I mean, this was a balancing where it was already balanced, the two half-cell reactions were balanced. What if you multiply one by 3 and the other by 2 to make the electrons balance? What happens then? What if you mix something and you've got choices? What happens then? Okay, so we'll come back next class and we'll go a little bit more into those challenging types of details. Okay, so we'll see you then. Hopefully your chemistry is going well for you, and we'll see you next class.